Up next, please welcome Grid Dynamics' own VP of Engineering, Ilya Katsov. Ilya leads engagements with a number of major retail and technology companies, focusing on big data, machine learning, and economic modeling. He's currently managing the industrial AI consulting practice that helps clients to become successful AI adopters and deliver innovative AI solutions. And today he is here to share the top data and AI trends to watch for scaling AI. Take it away, Ilya.
Hello, everyone. Thank you for joining the session. My name is Ilya Katsov. I'm Vice President of Technology at Grid Dynamics, and the session will be about scaling AI in production and top trends in this area. At Grid Dynamics, we are doing many different projects for large enterprises related to AI productization for marketing operations, supply chain, risk management, and so on. And in this presentation, I'm going to talk about 5 stories, basically short stories around our experience in these areas around doing these projects. And I'm going to talk about 2 main areas that are related to productizing AI at scale. The first one is how do we scale ML platform and what kind of ML ops capabilities we need to develop. And I'm going to present 2 case studies on that. And the second area that I'm going to talk about is how do we scale model operationalization, meaning how do we integrate models with the environment and how do we make sure that outputs of the models can be efficiently used by business users and downstream systems. So first, let's talk about ML platforms and ML ops perspective on the AI scaling problem. So most AI projects, they typically develop according to a standard model management lifecycle, which involves some data engineering activities, then model design, model training at scale, tuning, finally deploying model in the repository, managing model versions, and finally serving requests or batch workloads in production. And typically most ML platforms or open source solutions that are used to assemble ML platforms, they support a number of capabilities for this model lifecycle. This includes providing notebooks and managing multiple notebooks for data engineering and model development purposes, then capabilities for experiment tracking, capabilities for model training at scale in a distributed environment, model versioning, model deployment to production, and finally some model serving capabilities as well as monitoring. And these are quite common features that are supported by most modern cloud ML platforms, as well as open source solutions like MLflow. But at the same time, based on our experience with real-life projects, there are several not so common aspects of model lifecycle management that need to be addressed properly in order to run ML ops efficiently in production. The first aspect of it is how do we manage the entire life cycle of the models in a way that it can be represented as code and all the stages can be automated. The second aspect of it is how do we manage features across all the stages consistently so that features that are, for example, originally engineered and used for in the model development stage can be transparently used in model serving. And finally, what kind of domain-specific capabilities we need to develop all across the stages to support ML ops in different specialized environments, for example, environments related to computer vision or natural language processing. And I'm going to provide a couple of examples that illustrate how these MLOps capabilities basically can be implemented and why these capabilities are important. The first example is a project that we did for one of our clients actually several years ago, and basically the goal of this project was to create a machine learning platform that was able to support all this model lifecycle end-to-end. And basically what we implemented was a solution that developers, originally data scientists, could create model specifications like Python code that describes how models are trained and how trained models then served in production, for example, for point queries, and also create a number of descriptors that specify how different stages of feature engineering, model training, and all other steps are connected to each other. And then all these specifications could be committed into Git. And after that, we implemented basically an infrastructure that we used a continuous integration server to pull these specifications, pull these descriptors, then create Docker images based on these descriptors, as well as instantiate these pipelines in Kubeflow, and then run these pipelines on top of the Kubernetes cluster, because one of the key use cases for this platform was development of computer vision models, and these models were very resource consuming, of course, for their training. And it was important to provide this automatic infrastructure so that new environments could be instantiated in Kubernetes, and then models can be trained, and then these environments could be shut down dynamically. And the results of model training were committed to MLflow, and in MLflow, all experiments were tracked, model artifacts like binaries were stored, as well as model metadata. And the second part of this platform was around deploying these trained models into production. We basically integrated this MLflow with continuous integration server by developing a custom plugin for it. And then on this server, Docker images were pulled from the repository. These Docker images were created as a part of model training process, essentially. And then these images were instantiated in Kubernetes, and models were wrapped automatically into Flask services. And we also developed some capabilities for automatic metric collection, and then visualization and alerting around these metrics in Grafana. And this is basically an illustration of how the entire model lifecycle can be scripted and automated, and single commit into this pipeline to trigger all the stages from Docker images update to model training to deployment of models into production, and final serving of this model. And I would like to comment that this project was developed quite a time ago. Then this functionality was not fully available by in public clouds. For example, it was not possible to implement this flow end-to-end in AWS SageMaker or something. Nowadays, of course, it's more simple. Then the second case study that I wanted to share here is around development of domain-specific ML platform that illustrates some other aspects of the problem that I outlined in the beginning of this presentation. So in this project, the goal was to create an even more specialized model for computer vision use cases. And the first step towards it was to basically create something similar to what I described in the previous case study, basically create the model lifecycle management pipeline that included model development capabilities, continuous integration capabilities, model registry, and ability to deploy and serve models in production, as well as data engineering capabilities, data pipelines. But then, in addition to that, we started to implement more advanced services. One of the services that we implemented was around the development of features, and we basically created a feature store that was able to provide provide data through batch and point interfaces at the same time and guarantee consistency of this data. For example, the same features that were engineered in the model development stage, it was able to pull them through Pandas interface, basically, which is common for model development purposes, but at the same time, the same interface could be used to pull individual records in production for model serving purposes. And this way, this service basically guaranteed data consistency between model development and model serving, and the data could be accessed through one single interface in both modes. Then, in addition to that, we implemented a number of tools for data labeling, which were specific, of course, for computer vision use cases. So we deployed a number of data labeling tools as a part of this platform. Then, on the serving layer, we implemented an embedding index. Because many computer vision applications, they require to find nearest neighbors for a given image in the embedding space. And to support this type of use cases, we implemented a special service that was able to process such requests, receive embeddings from the upper layers and look up nearest neighbors for these embeddings. And finally, on top of that, we implemented an application layer that was able to, that provided a standard framework for typical computer vision use cases like image similarity calculation and nearest neighbor search in the embedding space, as well as object detection, segmentation API, and image classification API. And this is how basically the entire solution looked like. And as you can see here, many components were somewhat specific to the computer vision applications in this platform. And it, of course, was very important for efficient usage of this platform. Then the second aspect that I wanted to talk about is model development and operationalization capabilities. That is a kind of in addition to the model development lifecycle that we just discussed, assuming that we have ML platform that allows us to do model lifecycle management from development to production serving. We also need to think about some other challenges or some other issues that we potentially can run into when we integrate the model with the environment. And I would like to highlight two aspects of it. First one is how do we onboard new entities and new data sources, because it is important for some use cases to efficiently plug in new types of data or new metrics, new data streams into the model, into some installation that we already have in production. And the second aspect is how do we operationalize outputs of the models, which is, of course, also very important for many use cases that involve some downstream operations that might not be completely automated. For example, model outputs can be submitted to marketing teams or supply chain management teams, and it's important to think through how these outputs will be operationalized by these teams. And from the productivity perspective, one capability that is quite commonly provided by either ML platforms or quite commonly implemented using open source tools on top of ML platforms is AutoML, that helps to fine-tune model parameters and basically improve model architectures. And this is basically around improving the productivity of the model development stage. But other capabilities that, in our experience, are also important to think through is, as I mentioned, automatic onboarding of new entities and new data sources, ability to produce prescriptive outputs for downstream operations teams, and ability to learn and update models dynamically in production. And I'm going to provide three brief case studies that illustrate these capabilities. The first example is around automatic onboarding of new entities and new metrics. So in this example, in this project, we basically were developing an automated anomaly detection platform. And this platform was supposed to use in several different ways. Because anomaly detection capabilities are fairly generic and they can be applied to different use cases. So in this project, we basically aim to support three different types of use cases. The first one was data quality control. We plan to provide ability to send different metrics collected on data sets to this platform and detect anomalies related to instrumentation failures or MIT files or some other data issues. The second use case was around IT anomaly detection, so that metrics collected from systems and applications like CPU utilization or memory utilization could be sent to the platform and then analyzed to detect some anomalies and indications of failures. And finally, this platform was also supposed to be used for IoT anomaly detection in data that were received from sensors and other information about physical operations. And in this case, it was, of course, very important to provide automatic onboarding capabilities so that new metrics could be plugged into the systems. New models can be dynamically trained based on these new data streams and then used for scoring of ongoing metrics. And we spent quite a lot of effort and a lot of time developing these automatic onboarding capabilities to facilitate this process of onboarding new metrics and make it pretty much completely automated. And it was, of course, very important for this type of a solution. Then the next example that I would like to share is about improving personalization with prescriptive analytics. So in this example, we did a project related to improving marketing operations, and the initial state was that the company had multiple different predictive models for marketing operations that we use to quantify the lifetime value of a customer, propensity to churn, and some other customer metrics. But the challenge was that marketing managers, they actually struggled to combine these different scores and outputs of these models and produce some final decisions how these scores should be used to actually retain customers or improve customer lifetime value long term. And the goal of this project was basically to develop a next best action solution that was able to produce all these different scores, but at the same time combine them and determine the optimal action that needs to be taken with regard to individual customers or customer cohorts. And then this action could be either automatically executed through activation systems like emails or personalized website content, or these prescriptive outputs could be provided to marketing managers, and they can just review them and execute them more efficiently without making heuristic decisions about combining these different scores. And finally, last example that I'm going to provide in this presentation is around building a platform or the entire solution for dynamic interactive learning in production. And this is, I think, quite an interesting example because it's very different from pretty much everything that we discussed thus far in this presentation, because previously we talked about traditional approach to building models in the kind of manual mode, doing data engineering, model training, model deployment. But in this project, we used a complete reinforcement learning platform that is able to basically consume logs of transactional systems. And in these logs, for example, if these are transactional systems that interact with the users, and our goal is to produce some personalization policy. How do we personalize content or personalized offers? the users are exposed to. Then transactional system just write records in the proper format. What was the interaction with the customer? What was the customer state at a certain point of time? What kind of actions like offers or banners were shown to the customers, and what was the reward, basically the outcome? Did customer click on this banner, or did customer redeem the offer? And then basically the platform is able to consume these logs, then replay these logs again, reinforcement learning algorithms such as DQN, and then produce some policy that can be again evaluated in terms of its quality and efficiency, and then deployed directly to production. And actually, most of these stages can be done automatically, and the system can automatically consume these batches of logs and improve the policy and deploy iteratively new policies into production, gradually improving the quality of personalization and also improving customer engagement. And it was quite impressive project because it helped to drastically reduce the amount of effort that was needed to spend on development of these personalization models compared to manual stages. Yep, so that's it from me. I hope these 5 stories were helpful to you, and thank you again for your attention, and please feel free to ask questions if you have any.